topic to today's video is going to be writing and balancing chemical reaction equations. Something that I think most of you already have a fair bit of experience with. But we're going to take a few moments just to go back to the basics, just to make sure everybody's on the same page. Alright, so first thing that we have to recognize, we're going to look at a very simple example here. We're going to look at the combination of gaseous hydrogen and gaseous oxygen to form water. Alright, so it's water being formed from its elemental molecules. Now, what we have to recognize in any chemical reaction equation is that everything to the left of the arrow, where the arrow shows progress, everything to the left of the arrow is considered a reactant. The reactant is what we are starting with. Everything to the right of the arrow represents product. Product is what we are making. Alright? So, the other thing we have to make sure of when we write a chemical reaction equation is it's customary to put the states of the various reactants and products in. So in this case, hydrogen and oxygen are both gases, and water, when we make it, will be considered to be a liquid. So I make sure that I represent those states in the chemical reaction equation. Now the other thing that we have to think about with any balanced chemical reaction equation is that it has to actually satisfy the law of conservation of mass or matter. So that's why we balance the reaction equation. Now we know that we can neither create nor destroy matter. So what that means is in terms of atoms, we have to have the very same number of atoms of each element on both sides of the arrow. Alright? So that's very important. So let's go about this and check and see if we've got that. Let's start with hydrogen first. Breaking it down into the individual atoms, I have 2 atoms of hydrogen on the left. I also have 2 atoms of hydrogen on the right. So that tells me that the hydrogens are balanced out. They satisfy the law of mass conservation. Oxygen. I got 2 atoms of oxygen here on the left, but only 1 atom of oxygen on the right. So we see that the oxygens are out of balance. Now, the general rule here is that we want to balance the reaction equation with whole number coefficients. Okay? So what that means is that to get the oxygens balanced out, I'm going to put a 2 out in front of the water. So that suggests now that I'm going to make 2 waters. Now, once I do that, I have to recognize now that I've got 2 times 2, which is 4 hydrogen atoms. If I have 4 hydrogen atoms, I have to compensate on the left-hand side of the reaction. So I'm going to do that by putting a whole number 2 coefficient in front of the hydrogen. So now we've satisfied the law of conservation of mass or matter here. Alright, I've got 4 hydrogen atoms on the left, 4 hydrogen atoms on the right, 2 oxygen atoms on the left, 2 oxygen atoms on the right because the 2 distributes through. Alright, so what does this actually mean? Well, in terms of a balanced chemical reaction equation, I can think of this in 2 different ways. I can think about it on the atomic or molecular level, or I can think about it on the mole level. Okay, so if we look at it on the small level, where we're talking about atoms or molecules, what I'm really saying is that 2 molecules of hydrogen are reacting with 1 molecule of oxygen to give me 2 molecules of water. Now I can also scale that up to the mole level as well, because normally when we're working in the laboratory, we're not working with individual atoms and molecules. We're working with gram amounts of substances, which we can then think about in terms of molar amounts. So I could also say, by just scaling this up, that 2 moles of hydrogen can react with 1 mole of oxygen to give me 2 moles of water. So I can think about it either on the very small level or on the much larger level, the laboratory scale level. Alright? So I can do the same thing with another simple reaction that you may have seen in the lab. So in this case, what I want to do is make the oxide of magnesium, which is magnesium oxide, from its elements. Alright? So I'm going to start out with solid magnesium. I'm going to let it react with oxygen, and I'm going to make magnesium oxide. So this is actually a combustion or a burning reaction. You may have actually seen this before. If you burn magnesium, it gives off a very, very bright whitish light. Alright? So what you end up getting is sort of the ashy looking solid magnesium oxide on the other side. So again, we need to balance this reaction equation so that it satisfies the law of conservation of mass. So I've got one magnesium on the left, I've got one magnesium on the right. We're good with regard to magnesium. But I've got two oxygens on the left, only one on the right. We're going to use our whole number coefficient to make that right. So I need two magnesium oxides now. Now you'll notice the magnesiums are out of whack, so I'm going to compensate by using two magnesiums on the left. Let's check ourselves. Two magnesiums, we're good. Two oxygen atoms, two distributes through, so two oxygen atoms, we're good. All right, so again, two ways of looking at that. We're looking at that on the atomic molecular level. I could say that two atoms of magnesium react with one molecule of oxygen to give me two molecules of magnesium oxide. Or I could take it up to the mole level. I could say equivalently 2 moles of magnesium react with 1 mole of oxygen gas to give me 2 moles of solid magnesium oxide. All right, so those are two pretty simple examples here. Another situation that comes up is we have to sometimes balance out reactions that involve combustion. These are the same kinds of reactions that we talked about when we were dealing with empirical and molecular formulas. So let's take a look at a simple one here. In this case, we have the hydrocarbon called ethane. It's got the formula of C2H6. It's a gas. It can react with oxygen gas to give us the combustion products, which we know are carbon dioxide gas and water vapor. We get water vapor there because we know that when combustion occurs, heat's being given off, and that keeps the water in the gaseous state. All right, so let's see if we can actually balance this thing. So let's start with the carbons. I'm going to leave the oxygens to the end because the oxygens appear in multiple places. So as a general rule, we're going to start with the elements that only appear in 2 places instead of 3 places. All right, so carbon only appears once here, once over on the other side of the arrow. So we got 2 carbons here. So that means I need to balance this out by making 2 carbon dioxides on the right-hand side. All right, let's check our hydrogens rather. I got 6 hydrogens on the left. I got 2 on the right, so I better put a 3 out in front. So that should balance out my hydrogens. So now, let's take a look at the oxygens. Since we've already pinned down the carbon and the hydrogen here, let's count up the total number of oxygens that I've got on the right. I've got 2 times 2, which is 4, plus 3 more, which is 7. All right, so I got to balance out 7 oxygens on the left. Now the easiest way to do this is to say, okay, if I've got an O2 here and I need 7 oxygens on the left, I'm going to put a fractional 7/2 up front. All right, so I know that if I multiply 7/2 times 2, I'm going to get 7, and I know that's going to work out. But hey, I just introduced a problem here, because we said before that when we balance chemical reaction equations, we need to use whole number coefficients. But that's all right. I can fix this. If I have a 7/2 out front, and I want to turn that into a whole number coefficient, I just got to multiply through by 2. If I do it for the oxygen, I have to treat this algebraically, and I got to do it for every other element. So what I'm going to do is I'm going to put this whole thing in parentheses, and I'm going to multiply the whole equation through by 2 so I can get rid of this fraction. So if I do that, what I'm going to get is 2 C2H6 in the gas state, plus 7 oxygens, also gaseous, and we're going to get 2 times 2, which is 4 CO2s, and you will get 2 times 3, which is 6 waters, also in the gaseous state. Now, I'll leave it to you to go back and verify that these coefficients are indeed correct. You can do that by, again, checking the number of carbons on each side of the arrow, check the number of hydrogens on each side of the arrow, and check, lastly, the number of oxygen atoms on each side of the arrow. So we'll do more practice with this in class next time. See you later.